Okay, so hi everyone. Thank you so much for coming today. It is with great pleasure that I introduce today's speaker at the Colloques Mathématiques du Québec, Ryan Hynd. So Ryan had a unique introduction to mathematics and research. He began his undergraduate studies at Palm Beach Community College and later transferred to Georgia Tech to complete his undergraduate degree in applied mathematics. After participating in the Berkeley Edge program, he went on to receive his PhD at UC Berkeley under the supervision of Craig Evans. He was an NSF postdoctoral fellow at NYU's Courant Institute, working under Feng-Hua Lin. He subsequently moved to UPenn, where he has now risen to the rank of associate professor. Ryan works in analysis and PDEs with connections to optimization, geometry, and probability. In addition to his wonderful mathematical contributions, it has been a true joy to have him a part of my mathematical community, as he's always been incredibly supportive and encouraging of those junior to him. I'm thrilled he's able to visit us today, albeit virtually, to speak about sticky particle dynamics. Welcome, Ryan.
Cool. Thank you, Jessica. I'm blown away. That's a great bio, and just for the audience, I didn't write that bio, so I'm just really impressed. I might have to get a copy from you later. It's really an honor to be here speaking in this colloquium series. I love the idea of it, and it's also a great opportunity to tell you about some things that I've been thinking about. I know virtual talks can be hard. I know it's Friday afternoon, so my hope is that this won't be so complicated, and mainly to communicate the some of the key ideas and a few open problems. Feel free to interrupt. I didn't. Well, we'll see how we do at the time, but I definitely didn't plan on information overload. So there should be time for questions. Please don't hesitate if you have them. Okay, let's see here. All right, so a basic concept throughout the day will be that of a perfectly inelastic collision. Okay, so here we're typically thinking of a situation in the plane or in space where we have finitely many particles, but let's just say two to start out. And I've indicated those two right here, so M1 and M2. I've drawn dots. There's, these are point masses, but I've drawn circles here just to indicate these masses may not be the same. And the way perfectly inelastic collisions go, as you may remember from your early physics courses, are the two particles, when they collide, they form a bigger particle. The mass is sum, and the velocity of the new particle is chosen so that momentum is conserved. Okay, and here I'm assuming in the simplest situation where these particles are just freely moving. There's no other forces, so they move. When they hit, the masses join, and there's this new velocity. So this is the velocity of the new particle, and this was the velocity of the two particles coming in. And so this is just two, but of course there could be any finite number of particles, and they're analogous formulae. Okay, and so situation in the simplest form that I want to look at today is when we have a collection of particles, say finitely many, that are scattered throughout space, typically in R2 or R3, and they each get a nudge in a given direction, and they move freely. So they move in a straight line. Again, you can consider interaction. I'll say a few remarks about this at the end, but for simplicity, we'll just take them to move freely. And when they collide, they undergo, if and when they collide, they undergo perfectly inelastic collisions. Otherwise, they just move freely. Okay, so simple enough. And one thing that we'll do is write down some variables, try to keep track of what's going on. And so I'll write gamma as the position of point mass I at time t. It's a little ambiguous because say look at point mass 1 here, so M1. Okay, so M1 goes about its business and at some point collides with a few other particles, M2, M3, and M3. And but I want gamma 1 to stay with M1, wherever, whichever mass it ends up in. If it stays by itself, very easy. Otherwise, if it's collided, gamma 1 still keeps track of where M1 was. Hopefully the picture is okay. Okay, so in particular, say we look at M3. So M3 and M1 collide. And then at this point, gamma 1 and gamma 3, those paths agree after that collision time. Okay, and if there's no collision like gamma 5 here, well, it's just a straight line. Okay, and so these trajectories I'll call sticky particle trajectories. You might call this system, a collection of sticky particles, and these trajectories just kind of record, keep track in some sense of what's going on. There's a bit of information lost because the particles, they may have collided, but if you know what happens from the beginning, then you know what happens going forward. Okay, so I want to emphasize for you one key thing here is that these trajectories have this sticky particle property in the sense that if two trajectories ever coincide, which either means particles have just collided or maybe they collided a few moments ago, they remain stuck together forever, they be in the particles, or the trajectories coincide for all later times. Okay, just like in this picture, gamma I and gamma J, there's some collision and they stay together. And even if there's a collision later, no matter what happens, these two trajectories, they stay the same. They coincide thereafter, I should say. Okay, so that's one property. That one's pretty clear from the pictures. Now another one is what I call the averaging property. I probably need a better name for this, but I'm just going to call it the averaging property for now. And what it does here, so what is this expression? Well, okay, it's a sum weighted with the masses, and then I have here a function. H is a function of gamma I, and then I multiply by gamma I dot. Okay, I'm taking the right slope here, but this plus just means the right-hand limit of the slope, but there are only finitely many collision times, so gamma dot T plus is really gamma I T for most times. And I get the same expression, except S, I have S here, where S could be a prior time, a time earlier than T. Okay, so it looks a little.
What is H? What is H?
H is at this point is any function. Yeah, it's any function. Okay, so this encodes the conservation of momentum. So in these systems, okay, just this concept. I've had these particles, they're floating around space. If they collide, they stick together, and then you have this network of paths. Instead of saying, it's equivalent to say that at each time there's a collision, or at each time, the first time two trajectories coincide, there's some rule, the rule given by the law of perfectly inelastic collision. I can just state that this holds. It turns out to be equivalent. It turns out. In this, we'll see this, this what I call the averaging property. It'll come out later. It's related to, it's like a projection. It's like a projection that occurs in conditional expectation. And we'll see examples of it. That doesn't make sense to you. We'll see concrete examples going forward. Okay, so once we have these two properties, two key quantities that come about that are, I think, rather natural to look at. I'm definitely not the first to have looked at them, but two natural quantities are rho, which is the mass density, possibly dependent on time. Okay, and so rho is indexed by t. So for every t, I get a measure. Okay, and now measure, that already sounds a little technical, but you can just think very, very simply. So if you give me any region in space, say an R2 or R3 or an R, and you give me a subset, rho t just tells you what's the mass in that region. So at this stage, when everything is discrete, it's very, it's a simple object. Okay, but I could write it as, if I want to mathematize it a little bit, here I have this combination of masses and these Dirac masses at these trajectories. Okay, so there's rho. So for every time t, I get a measure. Okay, and likewise, I got v, which is going to be my velocity field. And really, all that I'm requiring of v is that it just points in the direction of where the mass is moving. Okay, so here, just to take a little snapshot of, okay, this should have been gamma I and gamma j. Sorry about that. So if I have two sticky particle trajectories, maybe they coincide at a given time. Well, the V just points in the arrow at where the mass is going. So V would be pointing in this direction, this direction, this direction. And then most importantly, when you get to a juncture, it points in the direction where the mass will now go. Okay, so I set it to be 0, otherwise it could be anything. It doesn't really matter. Okay, so it turns out that these two key quantities solve a certain system of PDEs. Okay, and the first, so this is called the pressureless Euler equations. This system, so I've written two equations here. If you're not familiar with it, you'll learn a bit more today. The first equation is is really a statement about the conservation of mass. You may have seen equations like this in physics or in electrostatics or dynamics. Certainly anything involving mass conservation, usually there's some expression like this. And the second equation is the conservation of momentum. And it's known as pressureless Euler because normally with equations like this, there's stuff on the right-hand side which reflects some sort of interaction between the particles or some sort of internal friction. And usually there's a term involving pressure because you have a continuum, maybe things are getting moved around and squashed and the particles are bouncing around together. But there's no pressure here. Okay, so it's a little bit different than the classical treatment. Although I'm going to write the equations in this form, and I'm going to say a little bit about that, which is it's a little dangerous because it could be a little technical, but I think it's somewhat instructive. Okay, so let's just look at the first equation for now, the conservation of mass. So that's here in this purple box. Okay, when I write this equation down, you and probably everyone, you're looking in a physics book somewhere. When you see this equation, you're thinking rho is a function, V is typically a vector field, and you just check a few derivatives and you get 0. Well, the objects that I have in mind, the rho and the V's, you see are pretty singular. I mean, for every time t, you're getting a measure for rho, and the V is some mapping that just lives on some lower dimensional thing at first. So it doesn't look like a great object, but it turns out that they naturally, from these rules, naturally satisfy the following condition. Okay, which they satisfy the condition here in this red box. So psi is a smooth function with compact support. Okay, all right. This is not the most geometric way to describe the conservation of mass. Normally you'd want to think of some region and see how it's kind of moved along, mass has moved along maybe, and make sure that the amount of mass that comes in and out is balanced in some way. But this turns out to be sort of more flexible for studying equations. And so whenever I write this equation, this is what I'm going to mean. I'm not going to come back to it, but I just want you to know behind the scenes, this is, it's almost like when you write an integral. There's a limit, there's all this stuff behind the scenes, but we just sweep it under the rug as long as we know what's going on. And this is motivated, by the way, because if you have a solution of this equation and you multiply the equation by what we call a test function, a smooth function with compact support in space-time, and you integrate by parts, you get an expression like this. And so it's natural, and a great exercise for students starting out in mechanics and continuum mechanics is to derive these sorts of equations using Green's formula and various integration by parts. But we're sort of going backwards, okay? So that's one technical slide. And so the next one is similar for conservation of momentum. This equation is typically a vector equation. If I'm in R2, say, or R3, it's typically 2 or 3 equations because the field, the V, the velocity field has whatever, D components, 2 or 3 components. And so if you took a dot product with this equation, so multiplied by phi, which is now a smooth mapping, that vanishes for large enough values of your spatial variables, and you integrate by parts, you get this equation. But as I said, whenever I write this equation, what I mean is this expression, okay? And I didn't point it out on the previous slide. But here, rho t here, it's a measure. So it's just something that I can measure sets with, or I could just integrate against. And so that's what appears here. Another thing I want to point out is the initial conditions are also baked into these as well. And so it gives us kind of a convenient way to interpret these rather singular quantities, but nevertheless pertinent to our study as solutions of equations. Okay, so far, what have we done? Well, we looked at the pressureless Euler. When we started with our sticky particle dynamics, we looked at pressureless Euler, and just a basic observation so far is that, well, there is a solution provided that the initial mass distribution is of this form, okay? And this is a mathematical way of saying, just I had some point masses thrown out there in space somehow, each located initially at some gamma I, point mass mi, and with any initial velocity, whichever directions that you wanted the various particles to go in, they would do so, and we'd have a solution. But nevertheless, just being mathematicians, we want to know, well, how, is this relegated to that situation, or more generally, can we find a solution? And of course, is it related to the physics and so forth? Okay, so since mass is, we expect it to be conserved, that's, our hope. You take it to be finite. This is an assumption, you don't need to. If it's finite and it's fixed, I just assume that the mass is 1. And so I write P here for probability measure on RD, okay? I won't say too much about that. Say a Borel probability measure. And V0 is just some continuous mapping. Any choice for the initial velocity, we like to know, can we solve it? Can we find a solution in the sense that I just described on those previous slides? And again, does it relate somehow to the physical system? Okay, so I could also ask this question from the standpoint of physics as well, in the sense that given initial mass distribution, somehow can I describe the trajectories that describe the collection of mass that moves around and obeys the laws of perfectly inelastic collisions, although it's a little bit fuzzy. What do you mean if it's a continuum? How exactly do those rules play out? It's a question, one that I think we haven't quite answered yet. So as I mentioned, or as I hinted at, I wasn't the first person to take a look at this problem. These equations have a long history. I'm not sure the first who really gave it a good study, but one person who's typically someone that we attribute as an early, someone who took a good look at these equations is this physicist, Yakov Zeldovich, one of the big physicists, astronomers of his time. And he was working really hard in the 50s and the 60s and the 70s. I mean, just extraordinarily prolific. I know a little bit about him just from looking around on Wikipedia and looking at some of his old papers. But he looked at these equations in a model for galaxy formation. So in the early galaxy, temperature doesn't play a role. Things are really cold. Things are moving around, and there's some sort of coalescing happening. And he took a look at this and did a lot of analysis. But it's typical in the physics world. I mean, he's looking at special solutions and trying to reduce the problem to something more tractable, as you see in this time. This is one of his papers that has, I looked online, had a lot of citation, and it is somewhat related. And what he did in that paper, I'll just cut to that right now. What Zeldovich did was he made, something that we observe pretty easily now, but probably back 50 years ago was sort of novel. He looked at the situation where there are few or no collisions and really studied that situation up until there was collisions or so-called shocks. And when there are no collisions, this corresponds to the case where, say V0 is the initial velocity that we want to prescribe. Well, this mapping here is injected, okay, for some interval of time, okay? And so just here in my schematic picture, I have particles moving around. This is purely schematic. Particles moving around and say X and Y, and I follow the straight line trajectory. And if they don't, there's no collisions and these guys are distinct. And if that's true for every X and Y, well, then this mapping here is injective. And so this is a special case. And again, he studied some particular examples, which we won't touch on. But the thing that he noted, probably obvious to the physicist, and we can write down, is that it's easy to write down a solution in this case. So given an initial mass distribution, what I can do is simply, well, if you give me a subset A of space and I want to know, well, what's the mass? Well, I just map back. I just pull, since identity plus TV0 is injective, or under the assumption that it is, I just pull that mass back and measure it under the initial measure, and that gives me a number. And well, mass is conserved. And you can always do this, by the way. I mean, given any family of maps involving time, you could always pull it back. You may not get a velocity like this because if there are collisions, it just doesn't work out. But if there are no collisions, you can do the same thing with the velocity. You just, wherever you are, you just pull back and see what was the initial velocity, and that gives you a velocity. And moreover, as a general rule, so rho here could be any initial measure, V0 could be any initial velocity, say continuous. I say continuous just because there's no question about integrability with different measures or whatever. So V0 continuous, you can check, it satisfies the equations precisely in the sense that, that I wrote down earlier. You can be more explicit with these guys. You can use change of variables, say if rho0 is a smooth density, and I'm not going to do that because it won't play much of a role in what we do. This is a special case. Some of you know the method of what's it called? The method of characteristics. Sorry, in PDE, solving equations along curves, and sometimes you can do it. This is one situation where you can. Another place where these types of equations come up is in the theory of optimal transport. Okay, different phenomena, but same equations. Okay, so in optimal transport, you typically have two finite measures with the same mass. Let's just say the mass is 1. So two probability measures, and you want to map, so okay, let's go back to Monge, because Monge is the one who started this. So you have a pile of dirt here, schematically indicated with the measure mu. Mu, think of it as being some density in the end. Maybe the dirt's not homogeneous. And then you have an excavation where also may not be homogeneous. Maybe the real estate, there's real estate, so some parts are more expensive than the other. And you want to map, you want to take the dirt in an optimal way to the excavation. And you want to do so in a way that kind of respects the densities involved, in the sense of whichever, if you take a little pile of dirt here and that has measure mu, that little pile, well, T maps it over to some real estate over here, which agrees with the measure mu. And there, T is measure preserving in that sense. And then you may charge a cost. If you take a point X to some other point Y here, there might be a cost associated with. Monge looked at the case where the cost was simply the distance. And if I'm in RD, the distance is simply X minus T of X, and you add that up over all the possible, X's in there, the little parts of mass associated with a given X, and that gives you an integral. It's the total transport cost. And again, it's natural to require that any such transport map is measure preserving, and you try to solve this problem. Okay, this problem goes back again to Monge many years ago. He looked at the case where there wasn't a 2 here, by the way, it's a 1. It turns out to be a little simpler to look at the case when here's a 2 here, just like L2 is a little bit of a simpler object than LP sometimes. And this problem, great history. Kantorovich picked it up in the early, or maybe in the 1930s or so, and embedded this into a larger class of problems. Invoked linear programming, duality, applied it to economics. I think even got a Nobel Prize. And then in the 80s, there was another breakthrough by Jan Brenier, who And I should say here, this problem may not even have a solution as posed if you don't so-called relax it. But nevertheless, Brenier identified a condition on these measures that once you have it, you can solve it. And so I think this was in 87 or so. And that condition was, say one of the measures is absolutely continuous, say mu, your dirt measure is absolutely continuous, so it has a density. So G, non-negative function, which integrates to 1. Then you can solve it. And in particular, an optimal map is the gradient of a convex function, in particular, a convex function that pushes mu onto nu, or satisfies that measure preserving condition. It's not even clear that you would even have such a map, but it's just amazing that you do, and it's convex. And again, it satisfies this optimality. Yeah, one of my favorite theorems. And a really special thing about this is that this object, this optimal transport map, can be used to design certain solutions of this pressureless Euler equation. So, okay, and you know, I probably shouldn't come to Canada, especially talking about optimal transport, without saying anything about Robert McCann. So, so McCann did play a role in all this, and he introduced a certain displacement, a certain interpolation between the measures, and it's of this form. So once I have that transport map, I can write down, think of it almost as a path between mu and nu, the dirt measure and the real estate measure. So mu is over here, nu is over here, and so okay, so here's, you know, one pile and where I'm trying to get to, and I can interpolate in between with a parameter t, say between 0 and 1. And when I push forward my initial measure with this mapping here, it really is an interpolation. If t is 0, it's just the identity. Identity pushes anything to itself. And when t is 1, then I get the gradient of psi pushes mu, and that just tells me that I'm over here at nu. And so in between, I get this measure rho indexed by time. And it turns out that this displacement interpolation, as McCann dubbed it, is a solution of the pressureless Euler. Although it is a collisionless solution, so it's not exactly the sort of solution that we had in mind. It tends, so you start with a nice smooth density and you move it to something, but it does so in a very organized way. In particular, it moves the mass along straight lines, and there are no intersections, there are no crosses. And it's the same sort of solution that Zeldovich had studied for short times. Okay, this gradient psi minus the identity is the slope of that line that I'm moving a piece of dirt into my excavation, and so the slope of that line was exactly gradient psi minus the identity. So it's the same formula that we had before. You may wonder, is this expression injective or invertible? And it is, because it's not only is this the gradient of a convex function, whoops, it's the gradient of a uniformly convex function, at least when t is between 0 and 1. And so it's a map that I can invert, and I could define this v. And from what we said before, it is a solution. Although I want to emphasize, this is where you're trying to go from one measure to another in some good way. And it turns out you can write a metric down, the so-called Wasserstein metric, and this describes a geodesic in that metric, constant speed geodesic, where this rho is indeed a constant speed geodesic. So here we have another example of a solution. Although, like I said, it doesn't quite do what we want, because I don't know of any way to build a solution of the initial value problem with it. Okay, let's go back to the initial value problem. Okay, so far we've been looking mostly in Eulerian variables. Okay, so those equations are set in Euler. So this means that for a given x and t, I'm looking to see what's going on, in the sense of, at time t, what's the mass density near x? What's the velocity of particles near x? Okay, the other point of view is following the trajectories around. And now I'll use x. Okay, I know I'll use the variable. This is a Lagrangian variable. And basically what this does is track particle trajectories. So you start out at y, and x, y, t tells you where the particle starting at y was at time t. And these two frames of reference or variable systems are related. May look a little different than you're used to, but in the context of this talk here, they're linked by these formula. Okay, so Rho mass density is typically the push forward of the particle trajectory. Sometimes I call it the flow map. And here I omit the y down here, the other variable. And so I just index the map by t. So you give me a t and it tells me, where did I take the initial configuration to at time t? Okay, and so this is the same formula as before with the push forward. So you just pull things back and measure according to the initial measure. And then crucially here, the velocity, well, it's the velocity. So the time derivative of x is simply v. And so this is how they're linked. And what I want to impress upon you today, the main thing is that, really the main takeaway from this talk is that, well, not only me, but I think there's a natural equation for the flow map. So in Lagrangian variables that describe the motion for pressureless Euler, even more general than I'm showing you now, but this is kind of, I think, the simplest, interesting case. Ooh, so I had it. Okay, that wasn't for me. Okay, so here's an equation now for the flow map. So again, let's say I give some initial mass density. Say it's a probability measure. Okay, so mass is equal to 1 in some continuous initial condition V. I want to find x of t. So x of t for every t, it's a mapping of Rd. If you want, take it to be, say, an L2 map with respect to that initial measure. And I want it to satisfy this equation right here. X dot is this right-hand side, which it looks a little weird. What is it? Well, it's naturally a conditional expectation. Okay, so at time 0, I want to be the identity. That just means nothing has happened yet. I'm just where I started. But the evolution, I claim, is naturally described by this equation. Perhaps the most physical way to describe this solution. You know, conservation and mass and momentum are very broad and describe a lot of things, but I think this equation will tell us a lot. Okay, so let me say a little bit about this equation here, because it looks a little funny, but it really is a conditional expectation in the sense of a conditional random variable. So what I mean by this is that at a given time, well, this right-hand side, or let's look at this equation. So I'm telling you what this whole thing is here. So what I mean by this is that for a given time, when I take the derivative of x, it's some function of x. Okay, so for the probabilists or people who have experience with conditional expectation, it's xt measurable. So you could think about it as also literally conditional expectation for the sigma algebra generated by xt. Okay, if you don't have experience with that, no problem. It's just, again, x dot is some function of x of t, okay? And for every h, say for every continuous and bounded function h, this average condition has to hold. So it's just like the average condition where we started out, where someone asked me, what was the h? It's almost the same exact condition, except in that slide I had s and t. Here I'm just having t and 0. But it's really the same thing. Okay, and again, if x happens to always be invertible, this just happens to be v0, x dot equals v0, and then there's nothing to check here because x dot is equal to v0. But when they're collisions, this is the best you can do. For those who know, maybe some who don't know conditional expectation, this is also kind of the projection or the closest. This expression right here is basically the closest in some sense, in the sense at the bottom of this slide, function of xt to v0. Okay, so that means x dot minus v0 in the L2 sense is as close as any other h. Okay, but sorry, this is what's here in the gray box is usually what's written, but it's also equivalent. So, so this is the equation, And obviously, the next thing we'd want to know is it at all related to the pressureless Euler system? And the answer is yes. Yes, 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 it is. Okay, so a basic lemma, and I should say this equation, I didn't invent this equation. I attribute it to both Sever and Dermoon. In the late 90s, they wrote papers independently. Dermoon from a purely probabilistic standpoint. Sever looking at it from more like, from the standpoint of conservation laws and sort of physical modeling. They both didn't write the equation like I've written it, but it's really there. Dermoon pretty closely, I will say. He worked with abstract probability space, and Sever worked with kind of projections, as I said before. But really, I think this is, I think it's fair to say, is the content of the idea in their paper. And they both realize, and I would say they both, I say they both, I'm guessing in the 90s, you know, maybe archive wasn't what it was, and both their papers came around the same time. I've never met either. I don't know if they know each other. I am familiar with both of their work just from getting it from Mass.net. So they noticed that if you have a solution, you define rho to be the push forward, as we've done a few times, and you choose V to satisfy this. So you define V implicitly. It turns out you can, almost by definition, but not with much. So before we just had a function of X here, but you can, it's not hard to just attach T as well. And both this rho and this V is a solution in the sense that we described before. So it's a sufficient condition. If you can solve the equation in the yellow box, then we have a solution of the pressureless Euler with the initial conditions that we want.
Sorry, what is IVP? IVP.
Initial value problem. I was running out of space. Initial value problem. Yeah. So I mean those integral equations, the ones with the test flow, it satisfies those for every yeah. So it is. So it works. So there's no doubt about this. I think this was a very nice observation for them. It still remains a question in my mind whether we can solve this equation. So that means the same question we had before, but now I just asked it for the specific, this specific equation. I don't know if it has a name. Sometimes I call it the flow map equation. I think it's the natural equation in Lagrangian coordinates for the pressureless Euler. And can we solve it given reasonable initial conditions? Maybe different initial conditions, different requirements than I have, but some non-trivial collection of initial conditions, some interesting collection. But I just write here for some mass with finite measure, say measure 1, and again, some bounded and continuous map. But you can obviously relax that. I'd be happy to know in this. Okay, for D equals 1, Dermoon, he wrote at least 2 papers on this. But in his first paper, he only focused on D equals 1, and he showed there is a solution. You know, he showed it was a nice proof, short argument, and I think it was quite nice. I should also say there's plenty known on the pressureless Euler in 1D, going back also in the 90s, in the mid-90s, I think maybe 94, 95, 96. E, Rykov, and Sinai on one hand, and Brenier and Grenier, I think around the same time. E, Rykov, and Sinai came out first, but I think they do comment on Brenier and Grenier in their work. So independently, they both came out with a solution and showed that there is a solution, and very, very nice work, influential work. And there have been many other contributors, as I've listed here: Savare, Nathalie Gangbo, Nguyen Tudorasco, more recently, Wes Dickenberg, many other papers on the case where D equals 1. They all have the same feature. None of them, or at least none that I know, someone may correct me if I'm wrong, or if they just think differently, none of them attack the equation directly. Almost all rewrite the equation somehow, use some different variables, almost like we did, rephrase the equation and then solved it. But no one treated it differently. None of those none of those methods or none of those tricks to rephrase the equation actually carry over in multi-dimensions. That's sort of the problem. What the equation for Dermone and Sever, it does, as I mentioned, it is a sufficient condition, but it kind of remains to be seen, does it really work? Sever would argue in his paper, his 98 paper, he does argue that there is a solution, and moreover, there's a so-called sticky solution, which has the property, kind of the sticky particle property, that if my flow map, if at a given S time S, if 2 points agree, then they agree forever after. And he insisted on this, and he says, hey, this is what's true. Fairly recently, maybe 2015 or so, Bresson and Nguyen, they have a paper which asserts that there are initial conditions for which no sticky particle, no sticky solution exists, no solution in the sense described by Sever. I tend to side with Bresson and Nguyen on this. I could understand their proof. I didn't learn a whole lot from it, but I could follow the logic. I don't exactly know where Sever went wrong. I have a guess, possibly where he might have gone wrong, but nevertheless, even if Bresson and Nguyen, if it's all there, I still think that there's still something to the equation, and it might be a lot to ask to produce a solution that exactly satisfies the physical requirement of sticky particles, but it wouldn't surprise me if something along these lines were true. Maybe not exactly in this form, or maybe you'd have to really be careful about the initial conditions and so on. But even though it's likely Bresson and Nguyen is right, and Sever and Dermone as well also published a proof that probably is not right. I think that the intuition, the idea that there is a strong connection is still makes the equation worth studying, and perhaps there's something to it. But it does remain a question. Okay, for the remainder of this talk, I want to give you just a feel for why 1D really works out. What's special about 1D for this equation? Okay, and I'll tell you a little bit at the end about how this even can be pushed further. Okay, so basic strategy for existence. And I only talk about existence, not uniqueness. Uniqueness is known, I should say, for this particular problem in 1D, but it's hard, and I don't know of any situation where it generalizes. Uniqueness, I think, is well, I'm not even going to touch it today. But anyway, so I'll give you a few steps, basic strategy here. So hopefully not technical, just an outline. Well, if you give me a general rho zero, it turns out that any rho zero can be approximated in this sense by measures which are convex combination of Dirac masses. So it's a technical thing, not too hard to prove, but it's a technical thing. The reason why this is advantageous is because given any measure of this form, this corresponds to how we started out the day. They're just finitely many particles moving around, and they're easy to describe what happens. I will say here, this rho zero k, this approximation, these mi's and xi's depend on k. I just don't want to write it in this n. I don't want to make the notation ridiculous, but basically each one of these rho zero k's is of the form of just finitely many point masses. And now we're just on the line. So particles are constrained to be on the line. They just move back and forth. They can just move right or left. And so when I look at the sticky particle trajectories, it's really simple. I can graph them versus time, and they're really simple. And here's a picture I just cut and pasted from my paper, and just put it in here. Another thing that's special about 1D is there's a certain stability. You see this picture that I have here on the screen? If I change anything ever so slightly, the masses, if I shift the masses around, the initial conditions of velocities, this picture just changes slightly. If I just move things slightly, there's a certain stability. In dimensions 2 or 3, there's an instability in the sense that if I change things ever so slightly, two particles that may have collided may not collide. And this instability, I think, is kind of at the heart of the difficulty. But nevertheless, let's stick with d equals 1. So we have our sticky particle trajectories. Well, two key estimates that are specific to d equals 1 are as follows. So one is what I call quantitative sticking. So we had this sticky property that if two trajectories ever touched, they would remain together. You know, they're married forever after. You could ask, well, what if they're close to touching? Are they going to be close for later times? And in 1D, it's true. And here's an estimate. It looks a little awkward, looks a little weird, but well, it's true, and it's the best one we have. And so that's what I offer you. And the next one is what I just call a stability. Well, trajectories stay ordered. You know, if on the line, if I have an initial condition xi and initial condition xj, well, the corresponding trajectories, well, they won't cross, so they'll remain ordered. But nevertheless, the distance between those trajectories, I can bound from above by that initial distance plus t times something involving the velocity. It's not a hard estimate when you sit down and think about it, but it does provide a bit of insight. And again, specific to 1D. And then I go back to what someone asked me about earlier, is the averaging property. I'm just rewriting the averaging property again for you here. So it's a, you know, gamma I dot and gamma I dot at t, gamma I dot at s, and then I do this projection, so to speak. It's the general statement of conservation of momentum. It does imply a certain energy dissipation, which makes sense. You know, if I have, say, two particles, you back in the physics lab, you know, freshman physics, if there's perfectly inelastic collisions, there's energy dissipation. Kinetic energy is not conserved, does not go up, but it does form a convenient bound for us. So what I can do now with this information is now define a flow map just defined on, say, the support, just whatever the finitely many points that define this measure, rho 0k, they're just finitely many point masses on the line that started out. I just define a flow map on that. Simply at any one of those locations, I just flow forward according to that sticky particle trajectory. And this gives me a map. And I can translate all that stuff I just said in terms of these maps. One is that stickiness, that same expression for stickiness. Now, this only holds on the support of rho k, which is finite. That doesn't look so good, but I'm going to fix that in a second. Okay, so I have this stickiness. Again, it just measures if you're close at time s, it estimates how far you are away at time t, where t is larger than s. Okay, and then I have that stability estimate, the one I just referenced for you. Okay, and again, particles stay ordered, but I have this estimate, and really what it does is it forms a continuity estimate. Because if I have two initial starting points, say y and z, well, the flow map that I just defined here, sort of ad hoc, doesn't seem like there's much to it, but that flow map is controlled from above by the difference of y and z, and then this integral. Okay, and now if I make the assumption that v0 is nice enough, say absolutely continuous, then this expression on the right here goes to 0 independently of k, and is basically a continuity estimate on these xk's. So whenever I have a uniformly continuous function, a basic factor, say if I have a function that's uniformly continuous on the interval 0 to 1, well, I could extend it to the whole line and maintain the same modulus of continuity just by, well, by some, I mean, various formula, but it turns out not to be hard. And so this xk, I could just extend it to the whole real line now instead of restricting its values to those finitely many points. And I get now a family of continuous functions. And, you know, just compactness is built in. And that's really what I'm trying to do is build some compactness so that I can get to, whenever I want to show something exists, I'm hoping to find some compactness. And so I can just use the compactness for continuous functions, just from you know, equicontinuous functions from Arzela-Ascoli. And it allows me to pass the limit rather strongly. So locally uniformly on R for all t's, it turns out. I didn't give you all the details, but this is probably the strongest statement that I can make. And moreover, the limit function or the limit mapping, so for every t I get a function, and so this gives me a mapping xt, it inherits various of the properties. Various of those properties are just carry over. I'm not going to rewrite them for you. The reason why this is important, and I wish we had something like this for higher dimensions, is when you go back to that averaging property, that equation we had, we wanted to pass to the limit there. Again, showing something exists, we need some, well, there's lots of ways to do it, but maybe you'd have some compactness or an approximation and then pass the limit in the object you want. Those functions H, which someone asked me about at the beginning of this talk, they're functions, they're continuous functions that I need to integrate against. And the only hope that I can pass to the limit is that if I have some reasonable enough convergence, and it turns out in dimension 1, it's just enough to get the convergence that I need. And so X infinity, it turns out to be a solution. There are a lot more details here, but the main thing is that the quantitative stickiness that you have in 1D, the stability, just give you a little bit more to get your hands around. And so the theorem that I'll state, one that I proved, the method was new, but like I said, it had been known to various authors in different contexts with more general initial conditions. But from what we've been doing here today, if you give an initial mass density, say it's a probability measure, that has a second moment and an absolutely continuous initial condition, then I can solve the pressureless Euler in 1D. And moreover, from some of those statements we made earlier, or I hinted at earlier, I can arrange this in a way that energy, kinetic energy, is non-increasing. And there's what we call an entropy inequality. And that's what's written right here. It's basically a one-sided derivative on the velocity field. It's really the same. For those of you who have some experience with conservation laws or entropy, it's really the same as that quantitative sticking. So in Lagrangian variables, the quantitative stickiness is equivalent to this entropy in Eulerian variables. Okay, and the last thing that I say, the very last thing I see, I'm running up against it here, is that if particles interact pairwise with some potential, instead of moving freely, there's some potential. Maybe there's gravitational potential, or they're in a, they could be in a situation, any sort of potential. They might wiggle when they get close to each other, who knows? Whatever the potential is, these are the corresponding equations for pressureless Euler. There's still no real pressure, just an interaction term. And analogous results hold, at least using the method that I showed you, that I sketched out to you here in 1D, providing that W is semi-convex, meaning W prime, it's lower bounded. Turns out that it's completely analogous, something that I've worked on, my very small contribution in this field. And I will say, like the method, the flow map equation, there's an analogous equation. So that all works out. I do wish I had more to tell you in higher dimensions, but for now, we'll just leave that as an open question. Thanks for your attention.
Thank you so much, Ryan, for a very interesting talk. Are there any questions from the audience? Please feel free to raise your hand or just unmute yourself. I have a question, Ryan.
Sure.
So you mentioned that, yeah, somehow in higher dimensions, there's little hope because of the lack of the stability condition. Has there been any work done in studying these models where maybe you have like stickiness only happening in one dimension? So you might imagine that you still have two-dimensional trajectories, but a one-dimensional stickiness condition, and whether or not you can understand the dynamics of this?
That's a good question. And I never thought about that. I thought it would be interesting, yeah, if there's something in between, say, 1 and 2 dimensions, something interesting. I think you can study it. See, the thing that happens is you have a complex model. So if I just throw out various particles, throw them out there, even randomly, the sticky particle trajectories, they're not hard to cook up, and we know plenty about them, but it gets to be, it's just sort of cumbersome. The equations in some way kind of give you a way to, in hopes to just understanding. It's almost like an average description of all these trajectories. I mean, it's special that since there's no pressure, the discrete formulation or the discrete situation with finitely many point masses just kind of gives you an exact solution. There's no mean field approximation that needs to be made. But nevertheless, we have these equations, and it's not too hard just to wrap your head around that. You can do other things, like you said, but where the equations play in, I don't know. I mean, maybe there would be an interesting set. Maybe it'd be sort of in between, analogously in between 1D and 2D. I don't know. Another, you could also try to add a little bit of size to the particles and see, how that play, or give them some sort of radius where they interact only if they're in some radius. I know Wilansky has done a little bit on that. But yeah, I think we're lacking a breakthrough. It's almost a bit of, what's a good way to put it? And actually, as McCann pointed out to me, but in higher dimensions, you expect not to get as many collisions, say in 2 or 3 dimensions.
Right.
And you'd figure that would help you, but yeah, we really haven't had anything definitive, I would say. It's my opinion as well. Some people might think that it's probably just too hard.
Mm-hmm. All right, great. Thank you. Are there any further questions?
I had a question. Is there anything, how similar or what can you do for elastic collisions?
Good question. So the thing about elastic, and I probably could have stood to write at least one slide on that. When you do elastic, there's a lot in between, but specifically with elastic collisions, you get kind of particles come in and come out, right, of the collision. Yeah. And there's no one velocity. So it's better described with kinetic equations. One where you have a position distribution, as we've been studying with this Rho, but maybe you have a distribution over both position and velocity or momentum space. And I could write down the equation it's just a transport equation. So you can write down the equation that describes that very easily. It's just, it's a linear equation. It's just, say if I called F the distribution in position and say momentum space or velocity space, it would just be the time derivative of F plus V dot the gradient of F in the X variable. And so you can always write down a solution there, even if you let particles just forgetting collisions, or you could have collisions be an option. That describes many scenarios. It describes what we've described today. These solutions are solutions of the kinetic model. And so the kinetic model is sort of the relaxation. You have lots and lots of solutions. When there isn't a lot of interaction, it's just sort of really simple in that case. And I think that's why. But your question is a good one. Something I thought about is among the multitude of those kinetic solutions, maybe you can select one that's most relevant here. Maybe there's sort of a canonical choice or a best choice or something along those lines. But that's just been an idea for me, not a theorem.
Okay, great. Well, if there are no further questions, let's thank Ryan again for a wonderful talk.
Thank you. Thanks for having me.